and welcome to mobile and wireless communication playlist. Today we're going to study about free space path loss model. First we begin with what actually path loss is. Path loss or path attenuation is the reduction in the power density of electromagnetic waves as it propagates through the space. The free space propagation model is a model which is used to predict received signal strength at a particular location when the transmitter and receiver have a clear, unobstructed line of sight path between them. Just for example, satellite communication systems and usually microwave line of sight radio links typically undergo free space propagation. As we know, in a radio communication system, the propagation of a modulated signal is accomplished by means of transmitting antenna, the function of which is usually twofolds. Firstly, to convert the electrical modulated signal into an electromagnetic field. Secondly, to radiate the electromagnetic energy in desired directions. At the receiver, we usually have a receiving antenna whose function is opposite to that of the transmitting antenna. It converts the electromagnetic field into an electric signal from which the modulated signal is extracted. It may be noted at this point it is useful to have a reference antenna against which the performance of a transmitting and receiving antenna can be compared. The customary practice usually here is to assume that the reference antenna is an isotropic source defined as an omnidirectional antenna, that is, which radiates uniformly in all directions. Let us consider an isotropic source radiating a total power denoted by PT, which is the power applied to the transmitting antenna. GT is the gain of the transmitting antenna. PR, amount of power received at the receiving antenna. And D is the distance between transmitting antenna and the receiving antenna. Here we have shown the transmitting antenna with the power applied PT and gain GT. Here it is the receiving antenna with power PR and gain GR. Following assumptions are made. We assume that the antennas are lossless, antennas are isotropic, and we assume that no obstacles are considered between transmitter and receiver. It usually suited for satellite and microwave communication. Here our aim is to predict amount of signal that can be effectively received at the receiver end, that is power PR. We have to predict the power PR. As we have considered an isotropic source radiating a total power denoted by PT, measured in watts, the radiated power passes uniformly through a sphere of surface area 4 pi d square, where d is the distance. Therefore, the power transmitted is defined by power density, which is equal to power received by surface area, which can be also written as PD, power density, is equal to power received PT divided by 4 pi d square, which is the area, surface area of a sphere. Area of sphere, because the radiation is isotropic, that is in a spherical form around the antenna. For a directional antenna, that is antenna which radiates in a particular direction, gain is higher in particular direction. Considering gain GT, we define power density is equal to PT divided by 4 pi d square into gain of the transmitting antenna GT. Now, observing from the receiver side, we know that the receiving capability of antenna is greatly decided by effective aperture of the antenna, which is the amount of power effectively received by antenna. That is, the effective aperture of an antenna is given by power received by the antenna divided by power density, written as PR by PD, power received by the antenna divided by power density. Or we can write PR, power received, is equal to PD into AE. Now we can write PR as we know PD is given by PT GT by 4 pi d square, so we can write it as PT GT by 4 pi d square into effective aperture. As we know, the relation between gain and effective aperture is usually given by lambda square by 4 pi into g, the gain. As we all know, the lambda is the wavelength given by c by f. So by this equation we get that the effective aperture is directly proportional to the gain. That means as we increase the effective aperture, the gain of an antenna increases. So substituting effective aperture in this PR equation, we get PR is equal to PT GT by 4 pi d square into lambda square by 4 pi into gain GR. We get PR is equal to PT GT GR lambda square by, here 4 pi we write it as 4 pi d whole square into losses. L usually use the loss factor, which is defined usually by filter loss, antenna losses and transmission line attenuation. So we get that the power received is inversely proportional to the losses. That is, as the losses increase, the power received decreases. This equation is called FRII'S free space equation. This equation usually tells that the receiver power decays at the rate of the square of distance between antenna. Received power is represented as function of distance between transmitter and receiver. Usually it is written as PRD. PTGT, here the term PTGT is referred to as an effective isotropic radiated power, EIRP, compared with the isotropic radiator. It is usually PTGT is usually referred as EIRP. Here we can write this equation as EIRP GR lambda square by 4 pi d square L. Usually its units are dBi, dB gain with respect to isotropic antenna. In practice, we usually use ERP, which is the effective radiated power. Power radiated is compared usually with the half-wave dipole antenna. Its units are dB gain with respect to dipole antenna. That's all about today's lecture. I hope you enjoyed the lecture. I'd like to thank you for watching.
Subscribe now and press the bell icon. Never miss an update.